Hello everyone, and welcome to Chapter 14, Kinetics of a Particle, Work and Energy. This module is conservative forces and potential energy, and we will also discuss principle of conservation of energy. Now, first of all, the first thing we need to do is that we need to understand the concept of conservative forces. What do we mean by conservative forces? And then I need to find the expression of the potential energy. How can I derive a potential energy out of these conservative forces? So the first thing is the definition of conservative forces. If the work done by a force is independent, and this is the main point, is independent of the path and depends only on the initial and final position, then it is classified as a conservative force. Meaning, I do not care how did you go from point 1 to point 2, I only care that what is the location of point 1, what is the location of point 2. Now, an example of this will be the weight of a certain object or a particle and the force of a spring. These are the two main conservative forces that we deal with in dynamic problems. To give you an example of a dependent force on the path that depends on the path, you can think of friction. The more friction you have, the more distance you travel. I could reach point 1, point A to B in a straight line, or I can go through curves. If I have curves, that means I'm going to cover more distance. More distance will give you more, friction as you go on. So friction is not a conservative force. So based on this, just to discuss these points in more details now on how can I convert this into potential energy. Energy is defined as the capacity for doing work. This is a definition that we discussed before in previous modules. Potential energy now is a measure of the amount of work a conservative force will do when it changes position. So it's about, again, the key point here is changing position. That's it. Kinetic energy, which we have seen before in Principle of Work and Energy, remember we used to call it T, which is half mv squared. It is the measure of capacity to do work associated with the position of the particle. That's why it has velocity in it. How do I change this velocity? Therefore, you can simply redefine these two energies as energy that comes from motion, as in velocity, is kinetic energy. Energy that comes from position, only location, whereas the location of that object is potential energy. Now, let's take the mathematical derivation of these. How can I write an expression for these? Let's look at the gravitational potential energy. For an example here, we consider the particle that is in the middle here, okay? Now, whenever you write potential energy of the weight, you must, and again, I insist that you must first define a datum. Now, datum is a line, horizontal line that you define, and it's up to you where to define it. You have absolute freedom where to put it. Just keep in mind that you have to choose something that is suitable, meaning that you know the distances. Don't pick a certain datum where you don't know what is the distance between that datum and the point. Pick something where you know the dimensions. So, the potential function for a gravitational force like the weight is the force multiplied by its elevation from the datum, which is the distance. For example, in this case, I have a particle on the right side. You can see here, it traveled along this curved path until it reached this point. Now, I have position 1 and I have position 2. Now, basically, if you are above the datum, then you have a positive potential energy. If you are below the datum, you have a negative potential energy. So let's look at position 1. My potential energy, we call it Vg, equals to plus W times Y. The weight times the elevation or the vertical distance. And it's positive because it's above the datum. In position 2, potential energy is minus Wy because it's below the datum. Now, the same example, if the ball was originally here and it dropped vertically until it reached the same location, potential energies will be the same. Will be here, Vg equals Wy, and here it will be Vg equals minus Wy. Therefore, you see, it's independent of the path. What I care about is the initial and final position. It was at that elevation, it went down to the bottom elevation. I don't care if you went with a straight line or you went through a curve. Okay, now, next we have the potential energy of spring. We call it the elastic potential energy. Again, the same thing. You have the spring. Now, you don't have to define a datum. We do things with respect to the unstretched position. If I have, let's say, a case where the particle is here, so I am pulling the spring by an amount of S. Okay. Now, what is the definition of S? I've said this in the module that discusses the principle of work and energy, and I will repeat it here because it's very important. The definition of S is crucial. S is the difference between the current length and the unstretched length. Okay? The unstretched length does not have to be something shown in the figure of a problem. It could be mentioned by writing that this spring has an unstretched length of this or that value. So let's look at this case. S will equal to this length, all of this, let's call it L. Let's call it, this is position 1 and this is position 2. So it will be, this is L1, the length at position 1, and let's call this L0. So S equals L1 minus L0. As simple as this. Look at, now what is the energy? Potential energy, elastic potential energy. VE equals to plus half Ks square. Okay. Now, let's look at position 2. So I am compressing the spring by an amount of minus S. Potential energy, the expression is exactly the same. It is plus half Ks square. Now, if you are wondering why is it plus not minus, because this minus, when it goes into the square, it goes away. So it is always plus here and there. So position 1 is plus, position 2 is plus. Now, the confusion sometimes comes when students try to compare the potential energy of a spring that is done here in this case with the work done by a spring when we discuss the principle of work and energy. And I will have a proof to discuss this to you for you. Now, let's imagine this case. I have a particle. I'm going to pick the datum here. Okay. The difference is S, and the spring is being stretched. So in this case, I have V equal to Vg plus Ve. What is Vg? I am below the datum, so I have minus Ws plus half Ks square. It's always plus half Ks square. Now, let's look at the work done in moving this particle. So I'm looking at U1 to 2. So it's going to be V1 minus V2. So let's write the expression. I'm going to show you that this ends up being exactly as the principle of work and energy. It's the same as the work done. So V1 will equal to, take the same expression here and write it twice for position 1, position 2. This was position 1, this is position 2. So it will be minus W, or basically, sorry, let's, I'm assuming position 1 is here, مثلا, and position 2 is, let's say, somewhere here. It moved twice, let's say. So this is position 2. So I'm going to have minus Ws1 plus half Ks1 squared, all of this in a bracket. And then, since I have minus V2, because I'm going from 1 to 2, and the work done 1 to 2, minus Ws2 plus half Ks2 squared. Take the W's together and the springs together, you end up with Ws2 minus S1 minus half Ks2 square minus half Ks1 square. And this is the expression, if you go back to principle of work and energy, this is exactly the expression we used for work. This is just to relate the two together. You do not need this in solving problem. I'm just showing you that the potential energy of the spring and the weight ends up giving you the same expression as the work done. Now, we are going to go to the conservation of energy. So I want to relate kinetic and potential energy terms together. And also I want to apply this principle of conservation of energy now to problems to see how does it work. Now, when a particle is acted, when do I use this theory? Basically, when a particle is acted upon by a system of conservative forces and only conservative forces. then the work done by these forces is conserved, and the summation of the kinetic and potential energies should be the same. Now, this means that the principle of conservation of energy works only if you have spring and weight, or one of them. It doesn't have to be both. But if you have any non-conservative forces like friction or applied forces, then you have to go with the principle of work and energy instead of conservation of energy. Now, keep in mind that principle of work and energy can solve any kind of problem, whether if it's conserved forces or non-conserved forces. But if you have only conserved forces, if you have non-conserved forces, then you cannot use conservation of energy. So, in this case, as I said, that the kinetic and potential energy summation should be the same, because yes, kinetic energy will change between position 1 and position 2, potential energy will change between position 1 and position 2, but the summation of these should remain constant. So T1 plus V1 should equal to T2 plus V2 should remain constant. Now, if I have more than one particle or one object, basically I'm just going to take the summation of these. Now again, I'm going to repeat this to avoid any confusion with students. This equation can only be used when I have conservative forces. If I have non-conservative forces, for example, friction, then I have to use the principle of work and energy. And another thing that I need to mention, that if you have only conservative forces, you can use this equation, okay? Or you can use principle of work and energy. It's up to you. But if you have non-conservative forces, you have no option, and you have to use principle of work and energy in that case. So let's start with the first example. Now, you have a spring that has a stiffness of 3 pounds per feet and an unstretched length of 2 feet. Okay? If it is attached to the smooth collar that weighs 5 pounds, and the collar is released from rest at position A. Find the speed of the collar just before it strikes the end of the rod at B. And you are asked to neglect the size of the collar. So you are dealing with it as a particle. Always, whenever you are reading problems that asks you to find the speed or velocity just before it strikes the end, don't think of it that if it reaches the end, it's going to stop, the velocity is 0. No. We are saying just before. So the moment when it hit B, it had a velocity in order to come and hit point B. So what is that velocity? So don't make the mistake of saying velocity is 0. Okay? So let's start first by identifying the datum. We're going to take, in this case, dimensions, as you can see, all are given. So I'm going to take the datum at point O, okay, which is the origin here. Now I want to calculate the gravitational potential energy of the collar at position A and B. I recommend that always compute everything separately. At the end, apply the principle of conservation of energy. So I'm going to start with point A. I'm going to say that we call it Vg, gravitational potential energy, for point A. Should equal to weight times distance. Now, is A above the datum? Yes. Then it's going to be a positive work, so potential energy. So it's going to be W, okay, multiplied by, let's call it HA, elevation at point A, which will equal to, the weight of the collar is given to me as 5 pounds. So it's going to be 5 multiplied by, what is the elevation of point A? It is 6 feet. So 5 times 6, this should give me 30 pounds. Now let's go to potential energy for point B. It's going to be V GB. Again, I am above the datum, so it's going to be positive. So it's going to be W HB, which should equal to, again, the weight of the collar is 5 pounds, and the elevation at B is 2 feet. So I'm going to say 2. This should equal to 10 pound feet. So I finished with the potential energy. Now, before I do the elastic potential energy, let me calculate the stretch of the springs at A and B. Need some calculation. Now remember, at position A, first of all, let me write it, S at A. Remember the definition of S that I told you? It is the current length minus the unstretched length. So, current length is O, A, distance between O and A, minus the unstretched length, I'm going to call it L0. This should equal to, now what is OA? I don't know OA directly, but I know the distances. I know that this is 1 feet. I know that this is 6 feet, and I know that this is 4 feet. So I can write this as square root of these distances are 1 square plus 4 square plus 6 square. All of this under the square root. So this is the distance between O and A, minus the unstretched length. Now, if you remember, just go back, read the problem in case you forgot. It says that the spring has an unstretched length of 2 feet. Therefore, it is given to me. And remember, I told you when I was explaining this earlier that the unstretched length could be given to you and not shown in the figure. So in this case, minus 2. This should equal to 5.28 feet. Okay, now let's do SB following the same approach. It's going to be OB minus L0. Now B, I have that this is 2, this is 1, and this is 3. Give it to me. So it's going to be square root of, we have 1 square plus 3 square plus 2 square. Now, just keep in mind that even some of these are negative values, like the one, you see this is positive x, and this is the negative x. You can see that this one is in the negative x. I don't need to put the minus in here because minus will go away with the square, so there is no need with these things. Dimensions, I'm taking only the absolute values. So back to this point, so this is OB minus unstretched length, which is 2. This should give me 1.74 feet. So now I have SA and SB. All I need to do now is compute the elastic energy of the spring. So therefore, now to calculate the elastic energy, I'm going to start with A. So V elastic at A, remember it is always a positive value, half K SA square. And everything is given now. So I have half. The elastic constant is given as 3. And SA, we just computed that value equals to 5.28 square. This should equal to 41.82 pound feet. Now V elastic B should equal to half K SB square should equal to half. Everything is the same, 3 except the value of the S, and we computed this to be 1.74 square, and this should give me a value of 4.54 pound feet. Okay. Now, finally, what I need to do is just apply the principle of conservation of energy. So I have TA plus VA should equal to T at B plus V at B. And that's why I say always don't try to solve everything inside this. If you try to do TA and compute VA, put the potential energy of the spring, of the weight and everything, you're going to confuse yourself. So I computed everything separately, and now all I have to do is just add them. So we're going to have half MA VA square plus, here I have VGA plus V elastic at A. This should equal to half MB VB square plus, plus I'm going to have the potential energy at location B, so it's going to be VGB plus V elastic B. Okay, now since the color was mentioned in the problem started from rest, so this one is 0, and therefore I have 0 plus, we have 30 plus 41.82. I'm just plugging the numbers from the previous calculations that we did, plus half. Now I don't have the mass, I have the weight, which is 5, so I have to divide by the gravity, 32.2, this is in British units, VB square, plus, here I have 10 plus 4.54. If you carry out the calculations for this one, you can find the final value for velocity at B, which should equal to 27.16 feet per second. And that's it for this. It's a very simple example, but it's a nice and very good example. I always like to start with a simple example that covers most of the, if not all, then most of the ideas, just to feel comfortable in applying these principles and know how to calculate these things, plus to build the confidence and the ability to organize the work. Now we go to a little bit more advanced of an example. So the 2 kilogram collar is released from rest at position A and travels along the smooth vertical guide. So smooth, that means there's no friction. Find the speed of the collar when it reaches point B. Now keep in mind that even though in the figure it looks that the spring is at the collar is at point C, but the problem is between A and B. Always when you have conservation of energy or even principle of work and energy, it is important to know the first and the final point. Okay, so also it asks you find the normal force exerted on the collar at this position. The spring has an unstretched length of 200 millimeters. Okay, so first of all we want to find the velocity at B starting from A, and at A so 2 kilograms is released from rest. That means at A I have no velocity. So as I mentioned in the previous example, we always start with organizing the work by computing everything alone. So let's start by just drawing some free body diagram in here. So let's say this is where I start. I'm gonna have something like this. Okay, so this is point A, this is point B. So at point A, this is my spring, and when the collar reaches B, this is my spring. And keep in mind that the distances are given. So the distance here, 0.4, sorry. Okay. And these are 0.2 each. Okay. Now, so let's start with this one. Let's start with the potential energy at position A and position B. First of all, I need to pick a datum. I'm going to pick A as my datum. You can choose A, you can choose B, you can choose this point. It's up to you where you want your datum. So I'm going to choose it at A. So let's do potential energy. Vg at A. I am at the datum. So basically I have nothing. So at the datum we have zero energy. Now let's look at point B. I am above the datum, therefore I'm going to have positive energy, so it's going to be W times HB, which should equal to, the mass is given to me as 2 kilogram. The weight has to be mass times the gravity, 9.81, times HB. What is HB? It is 0.4 going from A to this line, and then you have additional 0.2 here, so we end up with 0.6. Okay, and this equals to 11.772 joules. Okay, so this is the potential energy due to the gravity at locations A and B. Okay, now let's do the potential energy of the elastic springs again to draw the same figure. So this is my So this is position A, this is position B. So at A, this is my spring, and at B, this is my spring. And this distance is 0.4, this is 0.2, and even this vertical distance is 0.2. So now, first of all, let's find the S values. So at A, I'm going to find what is SA. It should equal to, this point is basically D. It was point D. So I need to find AD, which is the current length, minus the unstretched, which is L0, if you remember. So what is AD in this case? Okay, AD in this case is going to be, so this is 0.4, and this is 0.2 plus 0.2. So both of them are 0.4. So it's going to be square root of 0.4 square plus 0.4 square. This is the current length minus the unstretched length of 0.2. And this was given, if you remember in the problem, the unstretched length is 200 millimeters. Okay, minus 0.2. So this gives me 0.3657 meters. Okay, I'll do the same thing for S at B. This should equal to BD minus the unstretched. So this should equal to, at B I have 0.2 and 0.2 for the triangle. Okay, this is Pythagoras theory. So it's going to be 0.2 square plus 0.2 square under the square root minus 0.2, exactly the same way. And this will give me a value of 0.08284 meters. Now I can write the potential energy of the springs in this case. So I will go directly write V elastic at A should equal to half K SA square. The expression is the same, and you can see that I always write it directly without thinking. So it is half, spring constant is given as 600, and SA we just computed it to be 0.3657, and this should give me a value of 40.118 joule. And then V elastic at B should equal to half K SB square, which is half times, again, 600. And SB, we just computed it to be 0.08284. And this will give me a value of 2.0589 joules. Okay, now I have the elastic energy of the spring at both locations. I have the potential energy at both locations. What I end up with is just to write the principle of conservation of energy. TA plus VA should equal to TB plus VB. Okay, now in this case, I have half MA VA square plus, you can see that even though we have the values, we can directly jump in, substitute everything. I always like to organize my work and write everything step by step. So I have VGA plus V elastic A should equal to half MB VB square plus, again, potential energy due to gravity at B and elastic potential energy at B. Now, since we are starting from rest, again, initial velocity is 0 plus potential energy at A due to gravity was 0 because we were at the datum, and elastic energy, we computed it to be 40.118. Should equal to half, the mass is 2 kilograms, and I have VB square plus, now we have 11.772 11.772 plus the elastic energy was 2.0589. And if you solve this, it's a simple substitution at the end, you get that VB equals to, you'll get, of course it's a squared value, so you'll get, the roots will be one positive, one negative, we take only the positive value, so you get 5.127 meters per second, okay, which is roughly 5.13. Okay, so this is the first requirement of the problem. Let's go back to the problem. So determine the speed of the collar when it reaches position B. We found this one. Now the second part, it says also find the normal force exerted on the collar at this position. The normal force. So in this case, I'll need first at position B to draw the free body diagram. Okay, so at position B, let's look at the problem. I'm going to have, this is my collar. Now let's draw the free body diagram. I have the weight acting downward, WB. I have the normal force acting upward. Now keep in mind the collar was moving in the direction reaching point D, so this is my tangential direction, and the normal direction is towards the center of the curve, so this is my normal direction. And I also have the spring force, if you remember. So this is Fs, and the angle here is 45. Why 45? Because, just to remind you, the distances, this is 0.2, this is 0.2, so this line should have an angle of 45 because the two lengths are the same. Okay, so back to my free body diagram. So this is my free body diagram. So let's start with finding first what is the force of the spring, just to compute its value. Always it's good to do all these small steps separately rather than doing all of these together. So force of the spring is K times S at position B of the spring, which equals to, the spring constant is given as 600, and SB, remember we computed this earlier, so it is 0.08284. And this should equal to 49.71 Newton. Now, looking at the problem, since we need to find the normal force, when I do summation of forces, I'm going to have an acceleration. Normal force appears in the normal direction, therefore I need the normal acceleration. And if you remember from kinematics, this equals to v square over rho, V, I just computed this value previously. It is 5.127 or 1.3 if you want to approximate, over rho, which is 0.2. The distance between the point and the center of the curve, you can see here from B to this point is 0.2. So the radius of the curvature in this case is 0.2. Okay, so this will give me a value of 131.43 meters per second square. Now what's left is that to do summation of forces in the normal direction, I'm going to do downward as positive in the direction of the normal. So summation of forces in N should equal to M AN. So I'm going to have the weight of B, which is the mass, 2 multiplied by gravity, 9.81. What else? I have the normal force, so I'm going to say minus NB because it is acting upward. And then the spring force will have a vertical component acting downward. So it's going to be plus. The spring force was given to me as, we calculated it actually, 49.71. And then 49.71, and then the angle is the same. It's 45, so sine cosine does not matter, but you have to choose the proper one. It is this one. This is the component that you want, so it is sine the angle. So it is sine 45 degree. This should equal to M, which is 2 kilograms, multiplied by AN, which we just calculated to be 131.43. Everything is known except the normal force, and you can easily find it, and it's equals to 208.09 Newton. Okay, or a different way of writing it, I can say 208.09. Since we are putting it upward and it came as a negative value, so it's negative, it's minus of my assumption, so it's going to act downward. A lot of students get confused with this. They say it is a minus sign and downward is positive. How come it is down? No. This minus means that it is negative with respect to your assumption. Okay? So this is basically the second problem, and this covers the different cases of dealing with the spring and waves in different problems. And the last example also shows you how to use these results in connection with another problems in Newton's second law, or using also kinematics. I hope that this was helpful to you, and I wish that it will help you in your future studies, and I wish you the best in the future. Thank you.